Hello. Am I hearable? Yay. Been having some laggy issues with my class right before this one, so hopefully it will not be the case going forward. I can already see some issues already, so hopefully it's not too bad. All right, so announcements don't really have much. Test number 4 begins tomorrow. It covers up to and including 3.4. Nothing new there. I've had a few people sending me emails. I don't think that they're actually in this class, but just in case they have been, just like in regards to the midterm marking, if you have any questions about the midterm marking, again, feel free to email the appropriate people. But a lot of people have been emailing me because I've been dealing with questions 1 and 2, saying that they don't know why they lost any marks on question 1 when their answer is clearly different than what was in the solution. So just a reminder that the solutions are posted to the to Learn. So I strongly encourage anybody to look at the solutions before they start emailing us complaining, or not complaining is the wrong word, asking questions about their marking, very legitimate questions about their marking. To take a look at the solutions before you do that. That way, not so much that I'm trying to discourage people from asking questions, but at least to be able to ask questions in reference to what the answer should be. And just, clarify the questions. Usually it avoids a little bit of a back and forth that has to happen first. All right. So that's all I have in terms of announcements. If anyone has any questions about any of that, please do let me know. If not, will I be uploading Tuesday's lecture? I thought I already had. I thought I did it Tuesday afternoon. I wonder if I just didn't add it to the playlist. I'll take a look at that. I thought I already had, but I'll take a look at that as you're working through some of your practice problems. So if you remember last time, we talked about this really ugly expression that we proved right here, namely that the length of the cross product squared was equal to that nasty right-hand side expression. But then we noticed by using the geometric idea from the dot product that that the length of the cross product could be written in terms of just u times v times sine. And I said that that's going to be useful in applications, and surprise, surprise, that's really what we're going to be talking about for the majority of today, is how we can use this expression combined with some other ideas that we have in order to figure out the variety of different things that we're going to be looking at. So that's going to be one very useful property that we're going to be using. So let's first talk about some of the other useful properties that we have. So some of these we've talked about before, some of them we haven't. So just a reminder that the cross product is not commutative. Not commutative. So we switch the order, it changes. That being said, in a very specific way. Negative, we talked about that. That being said, the next two properties say that the cross product is distributive. So while it's not commutative, it is distributive. There's one more property word that we'll get to as well. Constants can be worked with nicely. You take the cross product with the zero vector, that's fine. And we also saw that rule that the cross product of any two things that are parallel, the cross product is zero. And we'll come back to that expression a bit more today. But it's these last two that we haven't talked about. So I want you to take the last two properties, take a look at them, and see if you can come to any conclusions based on those two properties. As with all tests, they're not directly cumulative, but they're often indirectly cumulative. Anyone notice anything about those last two properties? They definitely involve the dot product. For sure. Definitely involve the dot product. The first one, well, one of them is a scalar multiple of v and w. What about the other one? Yeah, the other one's a scalar multiple of v and u, and at its core, kind of, what do we notice about those two expressions on the right-hand side? And by the way, Tuesday's class, I just double-checked, and Tuesday's class is already posted. What we notice about these two right-hand sides? Maybe let me ask a simpler question to understand kind of, we get the, right. So, yeah, they give a vector in that plane. So if we take u crossed with v cross w, we get a vector in the plane determined by v and w. And similar for the next one, if we take w and cross it with u cross v, we get a vector in the plane determined by u and v. So we're getting that kind of stuff. But maybe even at its core, are those right-hand sides equal to each other? Are those right-hand sides equal to each other? So in our last two properties, yep, the u and the w are definitely just switched in the last two terms. But since u and w aren't the same vector, are those two things the same? No. No, those two things are not actually the same, which tells us what about the cross product? We knew it wasn't commutative. We know it's distributive. But based on the fact that the last two are not the same, tells us what? That it's not associative. And so it's for these reasons. So, for example, we talked about the dot product already, and we talked about how the dot product had this nice geometric use in R2 and R3, but we still did it for stuff beyond R3. And the reasons we do that is because all of these nice properties are true. So even though we lose the geometry, for algebra reasons, all these properties are true, so we still can use it for algebra reasons. But you'll notice we haven't done that with the cross product. The cross product has a nice use that it's perpendicular to the two vectors, and its length is going to have some nice uses today as well. But the point being is that because it's not commutative, because it's not associative, because it doesn't follow these nice properties, honestly, beyond just these geometric ideas in R3, we have no real use for the cross product. So the dot product we do for Rn, but the cross product is only something we do for R3. We're not going to be seeing it for any other dimensions because a lot of these properties like commutative, associative just don't apply and can mess things up if we ever tried to use it for more. So that's kind of the thing to take out of these last two properties, but also the fact that u cross v cross w, the first one, is a vector in that plane. The specific vector is a ugly dot product concoction, but it is a vector in the plane. All right, anyway, big picture out of the way, let's go back to a small picture. So here's a question. So given 3 points, so now we're going to start talking about applications of the cross product. Given these 3 points in our plane, or not necessarily in a plane, given these 3 points, there are 3 points of a parallelogram. So find the 4th point in that parallelogram and then find the area of the parallelogram formed by these 3 or 4 points. I'll give you a couple minutes. Give that a try. All right. Nobody has a fourth point yet? Nobody has a fourth point yet. All right, well, let's think of this geometrically speaking. Where does the D have to be? Even if we don't have the specific numbers, where are we going to get D from? Two, -1, -7. That is absolutely a value of D that works. So where did we get that from? All right, so if we take a look, here's AB. When we make ourselves a parallelogram, here's D over here. And the vector AD and the vector CD are going to be equal to each other. But is there anything special about using A, B, C, D in that order? No. In fact, what if we had, let's say, something like this and went off in this direction? We could have another D. Call it D2, I guess. And we could get our parallelogram looking like that. Is there any other ways we could form this parallelogram? Sure. How else could we do it? Yeah, so we get the D1 by starting at A and going AB plus AC. If we started at B, we could go BA and BC. But there's no reason we couldn't start at C and go CA and CB and create this parallelogram and have D3 down here. So there's no one answer to this. In fact, there's three answers to this. And we can get three possible points depending on which one we kind of think as the starting point of our parallelogram, not a parabola. Starting point of our parallelogram. We can get these right here. All right. So in terms of the actual arithmetic, we can find D1. So we know AB, as was mentioned in the chat, we know that AB is going to be equal to CD1. So we have A and B. In other words, our vector AB is going to be 1, 0, -1 minus 1, 1, 1 is equal to D1 that we're solving for minus C, which was 2, 0, -5. And now we just solve for D. The left-hand side becomes what? 1, -1, -2. Moving the other one to the other side, 2, 0, -5 is equal to D1. And so D1 is equal to the point 2, -1, -7. And we could do the same thing for the rest of them. For example, we could do BA is equal to CD2. And that would give us kind of the other way around. 0, 1, 2 is equal to D minus or D2 minus the same point. And that gives us D2 to be 2, 1, negative 3. And then something similar for the last one. Which two vectors are going to be equal in order to give us D3? So which two vectors are going to be equal to complete the parallelogram right here? Yeah, CB is equal to AD3, although that's not the only option. CA is also going to equal to BD3. So there's more than one way to do it, but we'll go with the one that was first suggested. CB is equal to AD3. So C was 2, 0, negative 5, but that doesn't matter because we're doing the other one. We're doing B minus C. So 1, 0, negative 1 minus 2, 0, negative 5 is equal to D3 minus A, 1, 1, 1. So that's negative 1, 0, 4 plus 1, 1, 1. Zero, 1, 5. So we get our 3 points, 3 possible points that are going to complete this parallelogram. All right. Any questions about how we can find the 4th point of a parallelogram given the first 3? It's all about equivalent vectors. Might have been a question on the midterm that dealt with that. All right. As for the area, let me draw the picture again. How do we find the area of honestly, any of these parallelograms? Yeah, base times height. Would AB plus AC minus A also work to find D? Absolutely, although that probably would involve more calculations than we did. But, because effectively we have one vector minus another to get D instead of 2 of them, but it still would work. Because AB plus AC would give us this vector. So AB plus AC equals AD. And then we could, once we have AD, we can subtract A to get D. Absolutely. All right, so how do we find the area? Base times height. Sounds good. It sounds like how to find the area of things. So here's the base. Here's the height. How do we find the base? Something specific about the line, of course. It's not just the, well, vector. It's not just the vector AB, but it's the length of AB exactly. What about the height? What about the height? In terms of finding the areas? To find the area, we just need one. It'll be the same regardless of which one we choose because it only depends on the 3 points. We don't need the 4th point to find the area. If you meant the actual finding the points, well, specifically I said there might be more than one. I guess in theory it depends on whether the question is asking to find a 4th point or find all the 4th points. So it basically depends on what the thing is. The projection of AC onto AB. The projection of AC onto AB would be this. That would be the projection of AC onto AB, which you could then turn around and do some subtraction to find the normal vector, yeah. The problem with the normal vector here is we're talking about the normal to a line, and this is not in 2 dimensions. So we don't have a nice way of doing it. So what's the height? How come AB is the base? I mean, in reality, any of these could be the base. I just did AB. If you wanted BD could be the base. Whoops, don't just use an eraser. BD could be the base, and then you'd have to drop this perpendicular to find the height. But any of the sides could be a base if we wanted to. How do we find the height? Trigonometry. Call this angle theta. The angle between the two vectors. That's something we've seen before. Yeah, so sine theta is equal to the opposite side over the hypotenuse. The opposite side is the height we're looking for. What's the hypotenuse of that right triangle? Yeah, the length of it, but yeah, the length of AC. And so multiply by the length of AC, and we get that the height is the length of AC times sine theta. So area is base times height. We get the length of AB times the length of AC times sine theta. And where have we seen that before? On Tuesday near the end of class. What's the length of AB times the length of AC times the sine of the angle between them? Yeah, that's the cross product itself. Is that right? No? Everyone thinks this is good? All right, sounds good to me. Even though it's not. Bingo. Yeah, it's not the cross product itself, it's the length of the cross product. Remember, the cross product is a vector. The area is a number. So if you ever write A equals the cross product, one's a number, the other is a vector, you're probably going to get more sarcastic responses than just, no, that's wrong. Maybe that's just when I'm marking. All right, so yeah, so the area of the vector, area is a number, the cross product is a vector. Right, so in other words, if we want to find the area of the parallelogram determined by 2 vectors or 3 points that give us the 2 vectors, then we just need the length of our cross product. So that's going to be our first application. So back to this example, we can find AB and AC. Again, that's just subtracting the points, and then it just becomes a cross product calculation. So before we find the area, let's first find the vector. So there's our IJK that we talked about on Tuesday. And it's a determinant calculation, so we can find it in any way we'd like. So what's I going to be multiplied by? Which determinant is I going to be multiplied by? eliminate row column. -1, -2, -1, -6. Row column. 0, -2, 1, -6. 0, -1, 1, -1. So we get 6 minus 2, so that's 4i. Minus 0 minus -2, that's 2j. 0 minus -1 is 1k. Which you can leave it like that if you'd like, or if we put it back into component form, we get 4, -2, 1. So any questions about how we found our cross product? All right, so that's a means to the end, but it's not the end. The area is the length of the cross product. So 4 squared is 16, -2 squared is 4, 1 squared is 1, square root of 21. So we can find the area of the parallelogram without ever having to find the height, because the cross product already takes that into account. All right. Any questions about how we did this? Why didn't we use sine? We absolutely use sine. Sine is where the formula came from. If you remember, the whole purpose of that gigantically ugly, awful expression was to show this. Right, so the length of the cross product already involves working with the sine. We don't have to multiply by sine again. Right. Any other questions? All right, well, if we can do a parallelogram, then there's no reason why we can't do a triangle. So see if you can find the area of the triangle through these 3 different points. All right, so at least even if you're not done the calculations, let's just get the ideas down. So what's the difference between doing the triangle and doing the parallelogram? Fair enough. In terms of the area, what's the difference? Yeah, the triangle is half the area of the parallelogram. So at some point, this hopefully was explained to you when you found the area of the triangle, period. But yeah, the area of the triangle is half the area of a parallelogram. If you want some geometric proof of it, the opposite sides are equal, and the last one is equal to itself, which means by side, 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 we have two congruent triangles that have the same areas. So the area of the triangle is only half of it. So instead of base times height, it's half the base times height, which means we can do everything we just did, just divide it by 2 when we're done. All right, so any questions about those ideas before we start calculating? All right, so we're going to be 1/2 the base times the height, which is 1/2 the area of the cross product. And so we can find our cross product. AB is 111, AC, a little subtraction. So another cross product calculation. Does it actually matter which order we take this cross product? Bit of a loaded question. So to find the area, does it matter which one we're doing? The answer is no. The answer is no, it doesn't matter. Now wait a second. The cross product isn't commutative. The cross product isn't commutative. So how can I possibly say that the order doesn't matter? Right, so if we did change the order, so if we take our cross product, AB cross AC, we get whatever we get. In this case, -6, 4, and 2. If we did it in the opposite order, we would get, don't write this down, but the negative of -6, 4, and 2, if we did it in the opposite order. And as some people are saying, if we take the length of it, is the length of some vector equal to the length of the negative of that vector? Because changing the order of the cross product makes it negative. Would the length stay the same? Yeah. So from strictly a finding the area point of view, if one student decided to do AC cross with AB and another student did it the other way around, it's not going to affect the actual area. Their cross products will be different. Ideally, they both do it correct and they get just the negatives of each other. But in terms of what the application, in terms of what the area is trying to do, it wouldn't make a difference. All right. Any questions about either of those ideas or how we computed the cross product? All right. So we get 1/2. The length of -6 squared is 36, plus 16 plus 4, which is 1/2 the square root of 56. No, it wouldn't matter. No, it wouldn't matter which vector we used as the base. So if we didn't do AB as our base, if we did BC as our base. If BC was our base, and we got, this triangle right here, and there's our angle, it would be BC, length of BC as the base, times the length of BA times the angle. So it would be the cross product of BC crossed with BA. And that would be perfectly fine as well. Some of the intermediate calculations would change, but you would still get the exact same area. You could have CA crossed with CB. That would also work. There's only one silly way to make it go wrong. What would be the silly way of doing that in a wrong way? Like you could have AC crossed with BC if you wanted to. Just don't do what? Yeah, just don't do like something like AC crossed with CA. Because if you use the same thing for both the base and the height, that's going to cause you problems. Specifically, the problem of getting wrong answers. All right. So, any questions about how we find the area? Either parallelogram or cut it in two and find a triangle? All right. So, these 3 points were not on the same line, but what would happen if they were? So what if these 3 points gave us 3 points on a line as opposed to what we would typically think a triangle would be? So geometrically speaking, the area should be 0, but is that what the calculations give us? Like if A, B, and C were on the same line, would AB cross with AC? What would happen? Because we may not know. It may not be obvious. And I highly doubt we want to check every single time we do this. Do we have to check if they're on the same line first? I mean, not that we couldn't do it, but it would be annoying. So what would we get if we took the cross product of AB crossed with AC? If all 3 of them were on the same line? Would it give us 0? Hopefully it would. Right. Yeah, if these are all on the same line, then AB and AC would be parallel to each other. They're going in the same direction. If they're all on the same line, then they're all going in the same direction, although I guess technically one could go in the opposite direction. But they're all going to be parallel to each other. And what do we get when we take the cross product of parallel vectors? What's the cross product of 2 parallel vectors? That's right, the 0, and so the length is 0. So even if they don't really form a triangle, I guess that's a philosophical debate, is a triangle with no area still a triangle? But regardless of how you feel about the philosophical debate, the nice thing is that the formula will give us 0 even if all 3 of them fall on the same line. AKA there's no height. Right. So if you have any questions about that, please let me know. If not, give this one here a try. Don't know. Whichever worksheets have vectors on them that don't involve a cross product would be my best answer to that. But I wouldn't know offhand which ones it wrote, which numbers they relate to. All right, so we want to take a cross. Wait a second. These are not things in R3. We can't take a cross product. That's a bummer. First of all, full disclosure, you could probably do this without any cross products and find the base and height using regular 2-dimensional geometry. But just to keep the ideas here, could anyone see a way, even though the cross product only works for R3, can anyone see a way of taking this question and coming up with a equivalent question that involves things in R3? So here's a warning before I do what we're about to do. 1, 2 and 1, 2, 0 are not the same. Just want to make sure it's clear. These are not the same. One is in 2 dimensions, one is in 3 dimensions. They are not the same. Things work very differently in 3 dimensions than they work in 2. However, the idea is the area of the triangle through the points 1, 2, 2, 3, and negative 1, 2 is the same as through 1, 2, 0, 2, 3, 0, and negative 1, 2, 0. And that's a C, not a bracket. So the points are not the same points, but the area of the triangle they'll create will be the same. Because, well, can anyone give me a good reason why? Why these 3 points? Yeah, area is 2-dimensional, that's absolutely correct, but these points are in 3 dimensions. Yeah, but we're not finding the length of AB and AC and all those kind of things. Yeah, it is because we're adding the same number to all 3. So in fact, if you wanted to do 7, 7, and 7, that's okay as well. Don't know why you'd want to, but it still would be fine. Why is that? Just out of curiosity. I mean, you could mindlessly just do it, but why doesn't this matter? I mean, I can understand why it makes sense that it doesn't matter, but why doesn't it matter? So when we look in 2 dimensions, we're in the XY plane. We look in 2 dimensions, we're in the XY plane that has no Z height. If we look at these 3 points, what plane do these 3 points go in? 3 points define a plane. What plane are these 3 points in? Yeah, they're also in the XY plane. Z equals 0. Z equals 0 for all of these. So there is no vertical height. So both of these situations, while they're using points in different ways, neither of them have that vertical height. Same thing, if this was 7, 7, 7, then we'd still have a plane that has no vertical height going on. It's completely horizontal. Completely horizontal. So while the points change, the points wouldn't be the same. The area of the triangle would stay the same. Because as somebody mentioned, the area of a triangle is a two-dimensional calculation. So there's no changing it if you put it in a 2-dimensional plane or a plane in 3 dimensions. It's not going to make a difference. All right. Anyway, long-winded explanation aside, if we're dealing with an area question in R2, we can just add the same third component to everything. 0 seems like the nicest thing to do, and now it becomes a 3-dimensional question, and we're fine. All right, blah, 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 blah. Let's do the calculations. So again, as before, area is 1/2 the cross product of AB with AC. And the nice thing about this is because the third components are all the same, AB, well, you tell me, what's AB? What is AB? The transformed AB that works with the cross product. 110. AC is -200. And so our cross product, notice how I'm not getting, A, B, and C are right here. IJK, 110, -200. And the nice thing here is there's quite a few zeros here, so taking the determinant is kind of nice. So what can we expand along? We can expand along the third column, for example. We could also expand along the third row. That works too. And we're left with 1, 1, -2, 0. And that's just going to be 2K or 0, 0, 2. And so our area is 1/2 the length of 0, 0, 2. And the length of 0, 0, 2. K is a unit vector, so 2K has a length of 2. And the interesting thing about this is if we did start in 2 dimensions and then transformed into 3, this last row is always going to be K00 every single time. So in fact, this is kind of a nice quick little way of finding the area in 2 dimensions through any 3 points. Kind of like it's not really a cross product, but a very similar kind of idea. All right, so any questions about how we can transform something in R2 to R3 for areas? I mean, the vectors themselves aren't changing, but in terms of areas, how we can kind of take a 2-dimensional problem and make it 3 dimensions? All right, speaking of turning 2 dimensions into 3 dimensions, let's find the volume of what we call the parallelepiped, which I expect most people to pronounce incorrectly, and I'm only 50% sure I did it correctly. Determine the volume of the parallelepiped determined by the vectors u, v, and w. I'll give you a few minutes to give it a try, and then we'll talk about the general ideas and do the calculation. The volume of this thing? Or just volumes in general? Base times height. Except the base is 2-dimensional. All right. So, first of all, a parallelepiped is what? I mean, this ugly monstrosity, but in terms of the ideas, what is a parallelepiped? I just like the word. It's a smushed box. Perfect. Yeah, it's a three-dimensional parallelogram. So basically, it's a shape where all six faces are parallelograms. And somebody asked what the volume would be, and the answer to that is it's the area, it's the base times the height, as everything should be. So here's the height. There's the height. And when we say the base for a three-dimensional object, when we say the base, so the volume is the area of the base times the height. So a two-dimensional object, the area, or a two-dimensional parallelogram is the area of the base being single-dimensional times the height. For volume, it's the area of the two-dimensional base times the height. So let's start with the area of the base. What's the area of the base? If we're taking this kind of plane at the bottom determined by u and v, what's the area of the base? So like we did that already, because it's a parallelogram. Yeah, the area of the base is the parallelogram. We know how to find the area of a parallelogram. That's u crossed with v. So the new thing is, what is the height? I'm going to blow that up. So here's w. So kind of here's the base. That's worse. So here's our base right here. Here's w. And we're dropping a perpendicular down. That's not better, but whatever. So what is that height going to be? Because it's hard to do it with an angle. Before we found this angle, and we did the length of w times sine theta. The problem is theta is no longer the angle between two vectors, so we kind of lose theta. So somebody's saying the projection of w onto the normal. Sounds good. I mean, this is kind of the stuff we saw when we were finding distances, right? We talked about the distance from a point to a plane. That's exactly what the height is. The height is the distance from the endpoint to the plane. And that's what we talked about in section 3.4. And we found that by finding the projection of w onto the normal vector. Except we weren't given a normal vector, so that might be a problem. We don't have the equation of the plane. And we weren't given a normal vector, so that's a problem. But that is the idea, is we want to find the projection of w, which is coming out of the plane, usually, and we want to project it onto the normal, because that's how we found this height back in 3.4. So we know what w is probably given. How do we find the normal to this plane? Well, that's u cross v. So u cross v is a normal vector to the plane. In other words, the height is going to be, well, not the projection, but the length of the projection. That's going to be the length of the projection, which is the absolute value of w dotted with the normal vector divided by the length of the normal vector. Since we're finding the length, we'd have two ends that would cancel off. So kind of as talked about in the videos, this n can cancel with one of these ends, and we're just left with w dotted with n over the length of n. Why is u cross v the normal vector? What is the direction of u cross v? Great question. What is the direction of u cross v? It's orthogonal to u and v. In other words, it's perpendicular to u and it's perpendicular to v, so that's what the normal vector is. All right, what was our, and as was just mentioned, that means it's w dotted with u cross v all over the length of u cross v. So here's our height. Any questions about how we used projections to find our height? All right, so back to the beginning, what is the volume? It's the area of the base times the height. The base was the length of u cross v. The height was this weird looking calculation in the numerator. Absolute value in order to make it positive, divided by the exact same thing as the base. So they cancel off and we get the absolute value of w crossed with u cross v. And there we go. Now this thing inside here is something called the scalar triple product. But it's a dot product of a cross product. And no, it's not distributive. You can't write it as w dotted with u cross with w cross, or dotted with v. That wouldn't work, for reasons that are hopefully obvious. All right. So that's nice. We can find a cross product. We can take the answer and dot it with w, and we're fine. Except I think we can do even better than that. How can we rewrite this in a nicer way? We weren't given points in the question. We were given the vectors. Although if we were given points, then we could find the vector. But we weren't given points. We were given the vectors themselves. All right. I claim there's going to be a better way to do this, but let's do it anyway. All right, so u cross with v. So back to, that was the idea. So to our solution, u cross with v is I, j, k. U was 1, 1, 1. 2, 3, negative 1. What's that? I times negative 1 minus 3 is negative 4. J is negative 1 minus 2 is negative 3. K is 3 minus 2, which is 1. Negative 4, 3, and 1. So there's our cross product. How could we check that we probably didn't make any mistakes? What could we do to kind of just check that? I mean, in theory, this could still go wrong, but it usually doesn't. How could we kind of check to make sure we didn't make a mistake in our cross product? Yeah. Take the dot product with U, we'd get 0. Take the dot product with V, we also get 0. And the chances of that happening coincidentally, even if you made a mistake, is unlikely. All right, and so we take W. So W is going to be, I'm actually going to, you don't have to rewrite this, but I'm going to for educational purposes. I'm just going to rewrite this as 1, 1, 3, negative 1, 1, 1, 2, negative 1, and 1, 1, 2, 3. And I'll come back to that later as to why. And so our volume is going to be the absolute value of W, whatever it is, negative 1, 0, 1, dotted with 4, 3, negative 4, 3, 1. And that's just going to be 4 plus 0 plus 1, which is equal to 5. So it's already positive. The absolute value is not necessary. And so our volume is going to be equal to 5. There we go. And we managed to find the volume of this three-dimensional parallelogram-y thing. All right, any questions about how we did that? Because I claim there's a slightly easier way to do these calculations. So I claim there is a slightly nicer way to do these calculations. That's the end. That's fine. Nothing wrong with that. But an alternative way to calculate. All right. So let's say we took W1, W2, and W3, and we took the dot product with, what's this, U2, U3, V2, V3, U1, U3, V1, V3. Whoops. And U1, U2, U2, U3. And we actually took this dot product, and we get W1 minus W2, and this should look familiar, and a lot of you are saying it in the chat, and that's wonderful. That this is just the determinant, but instead of using IJK, we can use W1, W2, W3, U1, U2, U3, V1, V2, V3. So, as crazy as it might sound, because everything here involved the cross product, in terms of setup, we don't actually need the cross product to do this calculation. And any order of the vectors also works for the volume. The determinant in W3 is wrong? Yeah, oh yeah, for sure. Of course. Thank you. Yeah, so this is just an alternative way of writing the scalar triple product. And the choice of where we put U, V, and W, again, the order of the vectors doesn't really matter. In terms of algebra, why does the order of the vectors not really matter? Why can we just switch up the rows? Why wouldn't that affect our volume if we just switched the rows? Exactly. Switching the rows is effectively switching the order in the cross product. possibly more than one time, but from an algebraic point of view, switching the rows just makes the determinant negative, but the volume is already taking the absolute value, so if it became negative, the absolute value would fix that anyway. We already needed the absolute value. So that's an alternative way of doing it. So we actually didn't need to do the cross product and a dot product. We could have just done a 3x3 determinant using these vectors. All right. And the last part of this that I want to mention is, what would it mean geometrically if the volume was 0? Geometrically speaking, what would it mean if the volume that we computed was 0? If this 3x3 determinant was 0, what would that mean? It's 2D. From a certain point of view, for sure, we could think of it as being two-dimensional. It'd still be an R3, but we could still think of it being two-dimensional. Maybe a bit more specifically, though. A bit more specifically, what's the height? Yeah, W is parallel to the plane of U and V. There is no height. There's no height, so W doesn't go above the plane. It doesn't go below the plane. W itself is parallel to the plane determined by U and V. So in fact, this is a backdoor way of answering the question whether three vectors lie in the same plane. So, see if you can answer this question. Do these three vectors all lie parallel to the same plane or not? So I'll give you a minute or two to try and answer that. Do these three vectors lie in the same plane? I guess technically they're vectors, so are they parallel to the same plane? No? Why not? They don't have to be multiples of each other. For example, if we had AB, AC, and AD, AB, AC, and AD are all vectors on the same plane, even though none of them are going to be multiples of each other. Oh, bummer. So yeah, so just saying none are multiples of each other does not work. That does not work in 3 dimensions. It's a fine thing to say in 2 dimensions, but beyond 2 dimensions, it does not work. So the idea is, if the volume is 0, they lie in the same plane, technically parallel to the same plane, because there's no height. The only way the volume of this thing can be 0 is if there's no height. Otherwise, if the volume is not 0, then there is a height, and therefore it doesn't lie in the same plane. Obviously, this isn't the only way to do it. You could actually find the vector containing two of them and then just check the other one, but this is just quicker. In other words, we take our three vectors, 1, 1, 1, 2, 3, negative 1, 1, 0, 4, and just ask ourselves, is this equal to 0? That's the question. And then it's just a 3 by 3 determinant question. So 1 times 3, negative 1, 0, 4. I'm expanding along the third row. And then I messed up the determinant. If we expand along the third row, that's 1, 1, 3, negative 1, minus 0, plus 4 times 1, 1, 2, 3. That's 1 times 4, plus 4 times 1, which is 0. And they lie in the same plane. So while the question took a backdoor way through cross products, we can actually just use a 3 by 3 determinant to determine whether three vectors lie in the same plane. All right, there is one more question I want to do. Not today, obviously, but one more question I want to do involving the cross product. So we'll see that starting on Tuesday, and then we'll be moving on to a completely new topic, which is kind of a merging of one section in chapter 1 and a section in chapter 4. So something to look forward to. If you have any questions, let me know. If not, have a good day.